Yes, sir, it is audible.
Uh, yeah, I'll do welcome address. Uh, Good morning, one and all. We start with a wonderful Sunday morning. On behalf of RMK Group of Institutions, the management of RMK Group of Institutions, I welcome you all. First of all, I welcome the principals of RMK Group of Institutions, the deans of RMK Group of Institutions, the HODs, the students, and parents, and Mr. Revathy, senior research scientist, NielsenIQ, Chennai. She is going to give a generic talk on natural language processing. I welcome you, ma'am. Now you take over.
Thank you, sir. Thank you so much. Um, so, good morning, everyone. I'm so happy Sunday. I am delighted to see that so many of you are joining us here on a weekend. As a student, I couldn't have imagined attending talks on a Sunday, but given the rapid advancements in technology today, I think it is crucial for us to stay updated, and we always take extra steps to make sure that we do it. Um, it's always a pleasure giving back to the academia and actively be associated with student communities. This is why our department has organized these tech talks for us to provide valuable insights and benefits to all of the attendees here. So we have attended other like insightful tech talks from delegates across various work streams. I hope today's session too will be equally beneficial, and that I wish we all have something valuable to take away at the end of the session. So I'll just go ahead and share my screen. Um,
Very difficult to communicate in terms of limited words. So here the
so can
conversation will
you
be with limited
give me
words. That
access?
means
I think
maximum number of
I'm
You
not.
are the
words
host,
that
ma'am.
we will be
You can.
listening could be
You are the
30.
host. You can
30
share.
words.
Thank
Maximum
you.
words could be 30 and minimum words could be 7 words. So 7 to 30 words we have to listen to, and we have to record our voice. So for that case, you have to test with your microphone, and then you have to test with the hearing. That means the audibility is okay or not. So then
Mm, I think I'm not able to share, sir. It says that the host has not enabled sharing screen or something like that.
Can you tell it right now, ma'am?
Mm, I think I am not able to. So can I send you and will you be able to share?
Oh, okay, ma'am. Right. Can you 30 seconds? Mhm.
So the visibility is okay, or do you want me to improvise with the font size? Is it fine with everyone? Is it fine with everyone? Okay, okay, yeah, thank you. So let us come to know how that means how the test is going to be conducted. So very simple process. Need not to worry about, need not to break your head and all for this reason. It is very simple. Only thing is we have to carry with our voice, that too judging our voice as per as if you are speaking to someone else. Yeah. So you have to think it is not reading task, it is not listening task. It is something where task which is given to us. So yeah, so let us find out how this tasks are given to us. So communication assessment, also known as cognizant speech assessment, is live for the batch of 2023 to 24. This is not only for cognizant, it is there for Accenture as well as Wipro. So all those companies are immediately just making the persons to be higher based on their communication skills. Okay. So many students are receiving the mails for the assessment test. So if at all you receive the
Yes, sir. Can you please go to the first screen? Yeah. Sorry, everyone. There's been a technical glitch with respect to me sharing my screen. Okay. All the formatting, the PPT has changed. Excuses for that. Excuses for the glitch and some waste in time. Um, so I think I've not introduced myself yet. I'm Revathy, and I work for NielsenIQ as a senior research scientist. And we here deal with a lot of problems around NLP space. Our organization is into consumer intelligence, so we analyze and decode a lot of market data, and we deep dive into trends to forecast what the future could look like for companies dealing with FMCG and CPG goods and many more. So let's get straight into the topic without further ado. I only had one day to work on this PPT, so excuse me if it's not aesthetically not that great. I did my best, but I'm sure you'll have a couple of more takeaways at the end of the session, and I'll be happy to take your questions at the end, should you have any. Can we please go to the next slide, sir? Can you actually put it on slide share? Um, can you slide share, sir, on the as a slideshow? Yeah, thank you. All right. So before delving into NLP, let's first see what the basis of machine learning is first, because there is a lot of noise and desperation in the industry surrounding AI and machine learning. Being a solid backbone of enabling AI, it needs proper reckoning. So please bear with me. The session could get a little mathematical because I always believe having a base strong, and the base for understanding machine learning and algorithms is to understand the math and the logic behind it, putting other theories aside. Also, a disclaimer: if there are any experts listening to this talk, I'm going to be oversimplifying a lot of concepts here for the benefit of time and simplicity. Each topic is a vast ocean on its own, and we cannot cover the nitty gritties of details in an hour. So let's just brush upon your high school math a little bit. So I hope you remember the linear equation, y equals mx plus c, where x is your input and y is the output, and m is the slope and c is the constant. You might have solved much more complex equations throughout your life now that you've landed in engineering, but this is a simple equation which made AI and ML what it is today, and all of its evolution surrounding it. So if I gave you the value of m and c, which is the slope and the constant, which you would have got through after various rounds of derivations, you will be able to find the output y for any given input x. So let's say I plotted a graph. So can you move to the next slide, sir? Yeah. So if I plotted a graph with this expression, and I got values of m as 2 and c as 1, and we can just let's say if x is 2, we'll be able to find what y is. It'll be 5. So we plot a point corresponding to x value as 2 and y value as 5. Similarly, if your x is 5, when your input is 5, your output will be 11, and we plot it on the graph. And when we connect these points, we get a neat straight line, which you'll be able to see if you move to the next slide, sir. Yeah, so that's basically it. If I mark any point in a line, or if I have any input and if I cross it on the line, we'll be able to find an output because the line is established. So in math, we solve linear equations, which is where a formula is established, and with the formula, we calculate an output given an input. In machine learning, we do reverse of that, where we are given outputs and inputs, and we are supposed to be deriving the equation out of outputs and inputs after having several different combinations of our slope values and the constant values in order to arrive at an approximate equation. So once you find the equation where we have a set of data, prediction is possible by applying a new or future input into the equation. So the graph or the model in reality will be an extremely messy congregation. So can you move to the next slide, sir? Next one, yeah. So this is how an actual data point in the real world would be represented as. The graph would be extremely messy, and in terms of equations, they'll not necessarily be linear. We'll end up being an extremely complex equation, not involving a neat line graph. Real world data is going to be something like this. So we need extremely complex computations in order to arrive at an equation which best represents the data that we're giving as an input. Next slide, please, sir. So this is a beautiful GIF, and AI experts here will appreciate how simple the illustration shows a model converging, yet how complex an implementation could get there. So the inputs that you see are different x variables in the equation, and you have these weights that converge to a point, which are the slopes m, and the bias is the constant c, and the output that you see the right hand of your screen is the y that we are able to get. In essence, all these complex mathematical computations that take place within are tweaking to reach an optimum value of weights and biases in order to arrive at a near approximate model or equation given inputs and outputs. Can we go to the next slide, sir? So going by this, we can see that ML model undergo mathematical computation. So it will obviously work only with numbers. And the input and output both need to be numeric in a data set like this. And it also needs to be tabular in a two-dimensional format. And since this data satisfies those conditions, it is really straightforward to model this. Though in reality, we'll be doing in a lot of checks and pre-processing to make it model ready. So all of these tabulated columns where we have a set of inputs and which is x1, x2, and x3, where we arrive at an output y is being modeled in machine learning through a technique called predictive analytics. Can we move to the next slide, sir? So sometimes the data will be tabulated. However, some of the inputs are not numeric. In cases like that, encoding will be done where each non-numeric value will be changed into a numerical representation, which is called categorical encoding. So here in this table, if you see, Toyota is being represented by 1, Ford is being represented by 2, and Mercedes is represented by 3. So instead of taking the column that has words or text is converted into a numerical encoded column. Can we move to the next slide, sir? So yeah, we will arrive at a column at a table like this, where you have all the data points perfectly numeric and it is simple to be modeled. This is to calculate or predict an insurance type given income of a person and a car type of a person, which is oversimplified because we have all of this as numbers. Can we move to the next one, sir? So since this is numeric, it's all easy, but things are not always numeric in machine learning, and we'll see the different types of inputs that we see when we solve a problem with machine learning. So one is the structured data, which is tabular, and the data is numeric or categorical, and we use predictive analytics for modeling the data. And up next, we have semi-structured data, where the data points are hierarchical and then can be represented in terms of graphs. There is a separate division of machine learning involved to learn data patterns and hierarchies called graph learning. It's a super important topic. In fact, I've spent around a year researching on the same, and I had tremendous learning experience there. The last kind of data is unstructured data, the data that is not numeric and not categorical, and they are represented as text and images to predict an outcome. So let's say you want to find if the scanned tissue images have tumor or not, or if a text which has a product review or a service review, it has a positive sentiment or a negative sentiment. We basically deal with inputs like this as well. So for text, we use natural language processing, which is our topic for today, and which is termed as a machine's ability to understand human language and process it for a certain downstream task. And for images, we have machine or computer vision, which is the machine's ability to scan through and look through an image for details. It is a vast ocean altogether, but since our topic today is NLP, we'll deep dive into and touch upon the basics and how it has evolved over the years. But before that, it's important to understand applications of NLP. So we have divided the applications into four different downstream tasks. So we do text classification, where a given string or a sentence or a text is classified into one of the several classes. It works in a very similar fashion of classification problem that we do in predictive analytics. And then we have text generation, where a text is generated as a downstream task. A typical example being all the GPT models that we're using today. There's also a text similarity problem where we arrive at use cases by analyzing similarities between two given texts. And finally, we have entity recognition, which is probably used where we want to convert unstructured text into a structured format. So the first one, as we see, is text classification, and one of the use cases is sentiment analysis. Um, and there might be numerous applications of NLP, but we all must understand that all NLP applications are nothing but prediction tasks. So text classification, as I said, predicts a label or a class into which a particular input belongs to. So if there are any reviews of a service or a product, you give them to a text classification model trained on various sentiments like positive, neutral, or negative. And the model will output if the review is positive, negative, or neutral. So this application is sentiment analysis, where a lot of organizations do work on web data or social media sites like X or Instagram or Facebook to see if their product is received well in the market, and what the general sentiment of the audience are like. And up next, we have text generation. Can you move to the next one, sir? So we have translation, machine translation here in place. As I said, this is a prediction task too, but it predicts words instead of labels to be generated depending on what a particular sequence of input words look like, and they also depend on the words that were previously generated, the previous output words as well. So they're used in applications like machine translation, where languages can be transformed or transcribed from one language to another, because of which I think we're able to freely blend in and move to different parts of the world, even if we do not know languages. We use applications like this to fit in and to communicate with each other, even if there are language barriers. We move to the next one, sir. So another application is under text generation is text summarization, where you have an entire document of several pages. And if you want to get a succinct or summarized version of that document, we do text summarization, which is again falling under the umbrella of text generation. Can you go to the next one, sir? And of course, we have speech recognition, which I think is most relatable and most used, where an incoming voice with speech is detected and understood by the machines by way of transcription. So this is also called speech to text, where we're using this in a lot of meeting applications, where meeting notes are basically transcribed out of the speech that the participants are talking, or even in your mobile applications where you have mobile assistants like Siri, where your phone chatbots are able to respond to a certain human speech that you are giving in as an input to the application. So the reverse is also possible, which is text to speech, where you input certain text and you have a computerized version of speech that comes out of it, which again falls into this umbrella. Can we move to the next one, sir? So this is another application called question and answering. So this is derived by analyzing the text similarity between the questions and the answers. So when we have a large document loaded into the model and we want to find a specific information in that document without scanning through the entire document, we go for question and answering, where we ask questions, and the model is able to fetch answers purely by analyzing each and every sentence in the document and seeing if a particular sentence fits to the question in terms of answer or not. And this is done by calculating the similarity metric between two different sentences that we have in the documents. Up next, we have chatbots. Next slide, please, sir, where this is another application of text similarity, where everyone would have experienced this across in most of the websites, where these chatbots or agents would respond to the queries made by users. So the answers are pre-programmed sometimes with rules in some cases, but thanks to advancements in AI, the answers can be retrieved if a chatbot is backed by common, frequently asked questions and knowledge-based articles, which reduces the workload of customer support executives, so that they are spared in terms of answering questions which are frequently asked and are too mundane to answer. Up next, we have entity recognition. Can we move to the next one, sir? So here we convert unstructured text into a structured format by recognizing categories of text provided in sentences and automatically mapping them to relevant categories. So similar tasks are done for entity recognition too, where you can see that the model can identify the category of the text it belongs to, and it flags as the same in the next. Can you move to the next slide, sir? So if you see, you have a chunk of paragraph, and each words are being flagged as a type of word. So you have a name that is flagged as a person, and you have a year that is flagged as a date, and many such flaggings and categorizing information like that. So that falls under the umbrella of entity recognition. And these are just a few out of a myriad applications of NLP that we're seeing and facing in our day-to-day lives, that has come as a direct effects of advancements in machine learning that we have right now. Can we move to the next slide, sir? So we see that all of these applications are heavy text processing applications. And when it comes to machine learning, we only can work with numbers. So how exactly are these texts handled by models in order to represent these texts by numbers and then model them? So the most straightforward thing a naive person would think of would be to just assign each and every word to a number. So you have a sentence which says, I have a pet named Tim. And you can just represent I as 1 and have as 2 and A as 3 and pet as 4, named as 5 and Tim as 6. So you can just see a straightforward substitution of each word with number, but the model cannot take this as an input because it does not convey any information about the word or the context of the word. And if you remember, the data for machine learning has to be in tabulated format, and this is not a tabular form. So this does not prove any usefulness with respect to models, because of as a result of which we have devised other methods of representing the text. Can you move to the next one, sir? So we then have this methodology called one-hot encoding, where we try to represent each word in a two-dimensional numeric format. So each word is represented by 1 or 0 depending on the presence or absence of the word in the sentence. So we have all of this sentences in the corpus, which is this is the first document, and then you have this document as the second document, and you have the third one and the fourth one, and so on. So you have a collection of all the words used in this corpus, which is called feature names. So if you see in feature names, they contain all the words that's present in the sentence. And you then have the document term matrix, which represents the presence or absence of a word in terms of 1 or 0. So in the first sentence, the word and is not present, so it is represented by 0. And then you have the presence of the word document in the first sentence, because of which you have it encoded as 1. And you also have the presence of word first, so it is represented by a 1 again. And you have the presence of is in the first sentence, so you have a 1 again. And the next one is 1, which is not present, it is a 0, and so on. So each and every word is being represented as ones or zeros. But here there is a downside, because there could be a humongous number of words in a document in real life. So you might be dealing with 15,000 different words. So if you're dealing with 15,000 different words, you need to have 15,000 different columns, which makes the numerical computations extremely heavy and inefficient. Also, if you've noticed, this just tells about the presence of or absence of word, but it doesn't tell anything about the word's importance. And it's a sparse matrix where you have a lot of zeros and some ones in between, but presence of these many zeros will confuse the model, which is why we will have a next technique of representation called as the bag of words. Can we move to the next slide, sir? So in bag of words, instead of representing a word with ones or zeros, you represent the word by the number of occurrence it's got. So in the second sentence, the word document occurs 2 times, which is why you see the number 2 in the second row, where the sentence is represented. And all of the other words are being represented by 1, because their frequency of occurrence is just 1. So this is called document term matrix, where we are recording the occurrence of words as to the number of times it is associated with, and so on, right? So if you still notice, it addresses the word importance problem, because the word is represented by a number depending on how many times it comes. So greater the number, more important is the word. But you will still notice that the matrix is sparse, it will have a lot of zeros. It also ignores word order. So there is another downside to it, where you have a lot of fillers, like and, words like and, is, the, and many fillers in an English sentence like that, which doesn't carry important context of those sentences. So they will be given more importance, and it doesn't fare the purpose. So we move on to the next representation, which is evolved from this, which is called the TF-IDF. It stands for term frequency inverse document frequency, where this considers the disadvantage of bag of words where the word importance is not established. So TF-IDF was it emphasizes on words that are frequent in a document, but are rare across all the documents in the corpus. So at the end representation, you will see that you will no longer have whole numbers representing the sentences, and they will start looking more like weights or vectors. in decimals. So they are useful in places where we are looking for applications in information retrieval or text mining and keyword extraction. So you will see that as these methods evolve in the process of converting words into numerics, you'll see that the sparseness getting reduced. So I can tell you how we arrived at this section of numbers from the document term matrix. So you divide each number by the number of documents that we have. So the one here is divided by 4 because there are 4 different occurrences of that word. And in 2 by 5, you see it's divided by 5 because there are 5 different occurrences of that word in a particular sentence, and so on. And we finally take a log of the density of words with respect to its occurrence in an entire document. And then we multiply the matrix which is present on your left to the matrix which is present down and arrive at the matrix that you finally see. I'm so sorry, this explanation is getting a little complicated, and I'm sure it wouldn't be taken or understood very well because I am not able to control the mouse and uh, teach it in a detailed way. But I'll just try my best. If you have any questions, definitely reach out to me. I'll address this topic in detail in person if you would want. Um, so up next, we have word embeddings. Can we move to the next slide, sir? Right. So, in fast growing fields of artificial intelligence, understanding and manipulating languages at a semantic level is crucial for developing intelligent systems. So, when I say semantic, it is important to understand a word from a context it's placed. So, for example, we have a word called bank. So, that bank, it can be both a financial institution or a river bank, depending on where I'm using the word bank. So if I say I am going to the bank to fetch money, it would refer to the bank as a financial institution. But if I say I am going to the bank to fetch some sand, I will be referring to the river bank. So um, embeddings are used for this purpose where a word will be represented by 2 different numerical representations depending on how the word is used. And this is essentially called semantic, and a lot of modern NLP models see to it that these words are well placed in terms of the understanding with respect to sentences. So, central to this capability of word understanding is the concept of embeddings, where each vector represent and process textual data in a multidimensional space. So, embeddings are very powerful and versatile in representing words and sentences. It is something that understands similarities between words. So you see that the dog is being represented by a 7-dimensional vector, which is 0 0.6, 0 0.9, 0.1, 0.4, minus 0.7, minus 0.3, minus 0.2, and so on. Similarly, you have numerical representations for puppy, for cat, for houses, man, woman, king, queen, and so on. So when you convert this 7-dimensional vector into a 2-dimensional vector and plot it on a graph, in a 2D graph, you'll be able to see that the dog and the puppy are placed close to each other because a dog and a puppy are similar in terms of how they look and how they are perceived as. Whereas a dog and a cat are farther than a puppy and a dog because a dog is more similar to a puppy than it is to a cat. So you see that the dog and cat and puppy and cat are placed farther on the graph. And then you have houses which are much more farther than all of these animals like puppy, dog, and cat that we are seeing. So that is the idea of deriving embeddings where a machine learning models are used to place words in an n-dimensional space to see to it that similar words are they appear closer in a spatial manner, and dissimilar words are thrown away farther which is just like clustering algorithms that you've come across if you are a data science student. So can we move to the next slide, sir? All right, so the embeddings also have another advantage of being able to arrive at semantical relationships between the words by the method of mathematical calculation. So we have king, man, and queen, woman. So if you look at the graphs, you'll be able to see that if you remove man from king, and which is represented by king minus man, it will be associated with royalty. And when you add royalty to a woman, it becomes queen. So if you subtract the king vector with a man vector and add it to a woman vector, you will see it arriving at a queen vector. And this is how the embeddings are devised by the methods of neural networks. You will also be able to see that you have a similarity, or the distance between a king and a queen being much lesser, and the distance between a woman and a man being much lesser, because king and queen have a common royalty context associated with them, and woman and a man have a public sort of a similarity associated with them. Whereas if you analyze in the other direction, you'll be able to see that a queen and a woman are similar words in terms of gender, and a king and man are similar words in terms of gender. So when you look from various dimensions, you will see that the words will be linked or similar. But when you see from a different dimension, you'll be able to see that the words could be dissimilar. So depending on the feature set of how we use the words and in which context we use the words, these embeddings help us in finding text similarities and deriving meanings out of sentences in the context that we're using. Can we move to the next slide, sir? So this is where we use text embedders, which are nothing but complex neural networks, which help us in arriving at these text embeddings. So the method it uses is it optimizes the words and places them at an optimal distance by measuring text similarities, like a cosine similarity. A cosine similarity is evolved from cosine distance that you would have studied in your vector calculus, where angle between two words represented in an n-dimensional space represent if a word is similar or not. So you have a lot of deep learning models which help us in framing these embeddings, which are Word2Vec, Glove, FastText, etc. They are pre-trained models that's available on the web that you can easily use in order to derive embeddings out of words and do a lot of downstream tasks to it. So Word2Vec converts word to vectors, which ultimately forms word embeddings. And sentence embeddings are created by doing mathematical aggregations on word embeddings, because words are a collection of sentences. So you either take a mean or an average of all the words to arrive at sentence embeddings, or you take a sum of all words embeddings to arrive at sentence embeddings, which are basically mathematical operations which help you get sentence embeddings. And then we have RNN and LSTMs, because we do realize that sentence embeddings are not just they are not sufficient to carry information about the sentence by aggregating words. So there are different sequence encodings that happen to sentences through RNNs, which are recurring neural networks, and we have LSTMs, which are long short-term memories, which keep the context in place even if a sentence is large or long enough in order to arrive at a context. We then have encoders and decoders. So the encoders are similar to RNN in a way that they convert input sequence into a sequence of vectors. And then we have decoders, where a sentence embedding converts it into sentences. So encoders and decoders, they form the basis of a transformer model. So a transformer model, so all these encoders and decoders that we are seeing, they are unidirectional, taking into account that we read sentences from left to right. So all of the information about the sentence and its context passes from left to right. But in real world, you'll be able to find the context of a word only if you read the entire sentence, because of which we arrive at bidirectional encoders, where the words are being read from left to right and then from right to left in an encoding perspective to arrive at the context of the word. So coming back at an example that I quoted earlier, I went to the bank to collect money. We'll have the encoding of a bank in a different format. And I went to the bank to collect some sand. We'll have the encoding of a bank in a different format, depending on where the word bank is used. And this has been done only by reading sentences from both left to right and right to left by the model. We also have several different transformer-based embeddings that not just have semantic relation, they also have contextual and long-range dependencies associated with the corpus. So it involves a concept called attention, which is a mechanism that helps the model to focus on important parts of an input text. So just imagine you're reading a book, but when you're reading a book, you just highlight a few points that you deem are to be important. So when you revise, you just get what are the important texts that you've highlighted, and then form your basis of understanding on top of that. So the attention and transformers, they work in an exactly similar logic. And when you have a very big text, for example, to translate from French to English, attention helps you to associate each French word with an English word, but also place the languages in such a way that they do not correspond to the position, and they stick to the grammar of each language by itself. Um, so that is about it. To summarize, can we move to the next slide, sir? So we have the evolutionary path that we have covered across. We have had one hot encoding, which just represents words as numbers in terms of its presence and absence. And then we have covered frequency-based encoding, which is the bag of words in TF-IDF, where a word is represented by means of how many times it has occurred in a document. Now, because it doesn't carry the semantic, we arrive at prediction-based encoding, where the word representations are derived from deep learning algorithms after having to predict words that correspond to its vectors. And then we have transformer-based encodings, which are much more complex than the prediction-based encoding itself, which again involves deep learning, but they have a lot more detailing and attention attached to it with respect to understanding the context and its sentences. So I do realize that all of these are extremely large topics by itself, and it takes several months to sort of have an exposure over this. And I've just covered them in one slides in an oversimplified format. So I hope it at least helps in a way that you have a context in terms of exposure to a topic. So whichever you find is interesting, you can delve deep and learn whichever parts of NLP impresses you. So if you see all of this, all of the evolution that we've seen has led to what we all use now every day, and the term that we are referring to and listening to every day, which are large language models and the GPT models that's been making advancements in AI space. Um, so it is only fair if I say that you'll be able to understand how a generative pre-trained model, the GPT models, work by understanding how historically we've evolved to go through all of these and then sort of understand how GPT works. So I think that is about it. But if you have any questions, please let me know. I'll be happy to address. I'm very sorry for the glitch. We hit a technical snag that I'm not able to present the slides. I think I would have done a much more better job in making you understand if I had had the mouse pointer to explain you through the details of mathematics involved. But if you are someone who is willing to take up a career in artificial intelligence, I would always recommend you to start with the logic or the math first, um, and then sort of understand the algorithms that go forward. You will be able to understand them in a much more intuitive way than just to digest the theories associated with the models. But that is about it. Yeah, and shoot away if you have questions. But thank you so much, CSE Department of RMKCET, for having this talk. It's always a pleasure coming back to the college I studied and be helpful. Um, so thanks for your time.
Pride alumni, first of all.
Mhm.
On behalf of our students, this is session. So, thank you for spending with our students, even though in holiday, that is Sunday is more valuable than everybody.
Exactly. Yes.
Thank you so much. Thank you. If you know, to give all the science topics, talk to you nine. On first of all, I thank our management to organize this kind of webinar talk period to enrich knowledge of our students. Then I thank our principals and deans and all research departments to support to organize this event. Finally, I thank all the faculty members and students to attend the event. Thank you so much. Thank you, sir. Thank you. We will leave.
Thank you, everyone.